We're going to solve this integral in two different ways, and it's a very informative type of an integral. You're going to learn a lot through solving it two ways and also seeing if the answers that you get are the same, because initially they're not going to look the same. There are two ways to solve it. One is my preferred way, as you see, the second way. But the first one, I'm going to use integral rules. If you have integral rules, first way is quicker and shorter. Here I'm going to separate the numerator and write it as two separate integrals, because integral of the sum of terms is the sum of integrals. So the first integral will be 1 over sine. Obviously, their denominator is going to be the same. And the second integral is going to be cosine x over sine x. As you notice, this one is cosecant, integral of cosecant, which is part of your basic rules. We're going to look at it in a second. And the second integral is cotangent x dx. After this point, you go to your formula sheet and you look at cosecant, and where's cotangent? And cotangent, right? And that's all you need. Okay, so the first integral is negative ln cosecant x, according to that formula sheet, right? Plus cotangent plus ln of sine x. Let's box that answer. So we have the answer to this integral using this first way. And as you can see, after this point, you just use the formulas from your 20 basic rules of integration. So that wasn't bad at all. But if you don't have the formula in front of you for those less common integrals, like integral of cosecant and integral of cotangent, a lot of people don't have those memorized because they're not as common. There's another way to solve this problem, which is my preferred way, because you don't have to remember things. You can just kind of use trig identities to solve it. I'm going to rewrite it, and I'm going to use this trick, which is called Pythagorean conjugate. And I'll tell you what I mean by that in a second. So a regular conjugate is the difference of squares will give you conjugate pair, right? X minus y and x plus 1 of y. So if you have one of them, you just change the sign and you have the other pair. So if you have this, you can multiply this by x plus y and you'll get the conjugate pair, and then you can rewrite it as difference of squares. Okay, you can have Pythagorean conjugate pairs. Nominator, as we said, will be difference of squares. So that will be 1 square, which I'm not going to write square there. 1 cosine square x. And the bottom denominator will be, I'm not going to multiply this denominator through. And this is y. Okay, this is part of your fundamentals. Know thyself and know thy trig. This formula is extremely fundamental in trig, and trig is a big part of your calculus too. So 1 minus cosine square, that is sine square. So I'm going to rewrite that as sine square in the denominator. I have 1 sine x here. And this is going to feel special because you can cancel one sign in the numerator and in the denominator. Now all I have left, and I want to rewrite it separately because Now I'm going to do a u sub, and before you do u substitution, you want to have an integral that's really organized. You don't want like things that are canceled sitting there when you're doing a u sub. Okay, so I'm going to get my u sub pocket. Now, the important question is, what do you assign u to be? You do have sine x dx sitting in the numerator. And you can probably tell that the derivative of cosine x is sine x. But also, I could have this whole expression, 1 minus cosine x, be u, because I know that after I take derivative, which is du, I'm going to kill the constant, right? Because derivative kills constants. So I will say that the entire denominator is u. Then du will be derivative of 1, which is 0, and derivative of cosine, and you still have that minus here, is minus sine x dx. And that is sine x positive dx. All right, I'm going to outline this. This is exactly what I have, so I don't have to express it in any way. I already have that. And this is my u, and this is du. I know how to take this integral because this is one of the basic rules. It is an ln integral. And I am going to back substitute, obviously, with the variable that I started with. Oh, no more integral because I'm taking this integral already. Absolute value of u plus the constant of integration, and I'm going to back substitute that 1 minus cosine x plus c. And I'm going to box that because that's the final answer. Now, the problem is that the first way that we solved gave us this answer, and the second way we solved gave us this answer. And at a first glance, they don't look like they are the same, but if you are ever wondering if you got the same answer when you solved something two different ways, whenever you're dealing with trigonometry, you can test a specific angle. For example, pi over 2 is a good angle to test because cotangent is cosine x over sine x. So you want to make sure that whenever you have cotangent or tangent, that you don't have the angle that you're testing that is undefined. Because if you tested pi, cotangent of pi is undefined. So pi over 2 is a good one to test. And then you see what you get, and you get 0. And then I plugged pi over 2 here, and I also got 0. And then I realized that they're the same. And I thought, can I do a math so that I can make this look like that? And I asked ChatGPT, and it said no, but I knew better that, of course, you can. So here, we're going to see how we're going to do that. So this is the answer that we got with the first way. This is the answer that we got the second way. And I'm going to do manipulations to this first one and make it look exactly like the second one and prove that it is the same exact expression said in other words. So you can kind of rearrange it, do a little algebra to it, trig substitutions, and it will look the same. So here, I'm going to start with the positive term. And by the way, let's get rid of the constant of integration because we don't need that here. All we're trying to see is if these answers are the same expression. Okay, so all I did here was I wrote this second and this one first so that I start with positive. So if you remember your log rules, anytime you have a difference, that is division. So it is sine x divided by this. If you had plus here, it would be multiplied. But when you have minus, it's divided. Next step, I'm going to, instead of having cosecant there, I'm going to expand it and say 1 over sine x. And instead of cotangent x, I'm going to say cosine x sine over sine x, right? So since they share a denominator, I'm going to combine this in the next step. Okay, so you have 1 plus cosine x over sine x. Well, this sine x will come up here and it will be sine square x. So this is the expression that you have here. Well, remember we said that sine x, sine square x equals 1 square minus cosine square x. That is what I'm going to rewrite sine square x as. And remember that this is the difference of squares, right? This is squared, this is squared. So I'm going to write it as conjugate pairs. Oh, ln. And you probably can see already that I have 1 plus cosine x in the numerator as well as in the denominator. And of course, I'm going to cancel them. I guess I'll do that. I'm going to cancel this with 1 plus cosine x. So all I'm left with is ln of 1 minus cosine x. ln of 1 minus cosine x. And I want to change the color and have it the same so that you can see that we started with this expression and we got this expression. So in fact, these two expressions are the same. This is expressed different, or this can be expressed as ln of 1 minus cosine x. And I think that's quite beautiful because, as you can see with trig identities, you can prove that here. So if you have the formula for integral of cotangent and integral of cosecant here, then this way is simpler because it's faster and it's shorter solution. But if you don't have the formulas in front of you, you probably don't remember these integrals, but you most likely do remember how to take this integral. And after you see this 1 plus cosine x, or even if you see 1 plus or minus sine x, you should automatically think, should I multiply this by its conjugate pair, which is the same thing but with an opposite sign.